Okay, so hello everyone. In this video, we will see very important question on deadlock that has been asked in GATE exams. In this video, first we will see a banker's algorithm question and then two deadlock avoidance questions. So without wasting time, moving forward to problem number 1, banker's algorithm with safe sequence. Now the question is on banker's algorithm, in which we have 4 processes and 3 resources. There are 3 types of resources given like E, F and G, and 4 processes are given P0, P1, P2 and P3. Other than this, they have given us the allocation metric. What is the meaning of allocation? The value 1 means 1 resources of type E is already allocated to P0. Similarly, 1 resource of E is already allocated to P1. 1 resource of E is already allocated to P2 and 2 resources of E are already allocated to P3. The resources are already allocated to processes in the past. We can call it allocation, like we can also call it assignment. Now the next is the maximum matrix. Like what is the meaning of maximum? We can call it maximum need also. Maximum need means the processes are already telling us that what is their maximum requirement, how many resources they need to get executed completely. Like P0 is saying it need 4 unit of E, 3 unit of F and 1 unit of G. If P0 gets 4 unit of E, 3 of F and 1 of G, total of these resources, then it will successfully execute. Now because we can fulfill the need of P0 if we provide the exact numbers, same logic applies for P1, P2 and P3. The third thing given is available. Available means, as we have already seen, some of the resources are already allocated. Out of all availability, I have already allocated some resources to the processes. What is the remaining with me? What is the available or current available? You can call it current availability also. At present, how many units of E am I having? 3 units of E, 3 units of F and 0 of G I am having at present. So the system has 330 current availability. Now the question is asking us to find whether there is a safe sequence or not, whether this will create a deadlock situation or not. So we will analyze this step by step. To analyze this problem, we first need to find the remaining need of every process according to each resource. For each resource type, we have to find the remaining need. What is the remaining need? Remaining need means maximum needs minus allocation. This is the meaning of remaining need. If a process is saying my maximum need is 5 and I have already been allocated 2, then what is the remaining? 5 minus 2, there is 3. Very simple concept. Okay, so you have to calculate for each process the remaining need. Let's calculate step by step. For P0, for resource E, maximum need is 4, but already 1 unit of E is allocated, so remaining is 4 minus 1 is 3. For resource F, 3 minus 0 is 3. For resource G, 1 minus 1 is 0. So P0's remaining need is 330. For P1, E is equal to 2 minus 1 is equal to 1, F is equal to 2 minus 1 is equal to 1, and G is equal to 4 minus 2 is equal to 2. So P1's remaining need is 1, 1 and 2. For P2, E 1 minus 1 0, F 3 minus 0 3, G is equal to 3 minus 3 0. P2's remaining need is 0, 3 and 0. Now for P3, 5 minus 2 3, F 4 minus 0 4, Z 1 minus 0 1. So P3's remaining need is 3, 4 and 1. Now what do we need to check? This is the remaining need which we have to fulfill, which the system has to fulfill. By having this current availability, can we fulfill the need of any of the processes? Check carefully. By having this current availability in my hand, can we fulfill the need of P0, P1 and P2 and P3? If yes, we can proceed further. If no, then we can simply say that there is a deadlock in the system. We will find safe sequence. To check this, remaining need should be less than or equal to current availability. This condition we have to check. Remaining need should be less than or equal to current availability for all the resources type E, F and G. Let's check for P0. Remaining need is 330. Now current availability is 330. So we can fulfill the P0 need. So yes, we can fulfill the need of P0. Let's also check P1 for comparison. P1 requirement is 1, 1, 2. Can we fulfill this? For E, it needs 1. We have 3. No problem. For F, it needs 1. We have 3. No problem. For G, it needs 2. But we have 0. This is the problem. So you don't need to check only for a single resource. You have to check for all resources type E, F and G. If this condition is fulfilled for any resource type, then only you can proceed. If it's fulfilling only 1 or 2 processes, like let's say E and F, and G is not fulfilling, then no. For all resources type, this condition must be fulfilled. So for P0, the condition is satisfied. P0 will get the resources, and when we provide the resources to P0, it will get successfully executed. When it gets successfully executed, executed, the process will terminate, and when the process terminates, it will be removed from the system. Whatever resources were already allocated to P0 in the past, they will be returned back to the system. So what resources were already allocated to P0? 1, 0 and 1, E 1, F 0 and G 1. So this 1, 0, 1 will be added to the current availability. Current availability was 330. I provided 330 to P0. P0 got executed, but whatever resources were already given to P0 in the past, I have to take back those also. So what will be the new current availability? 3 plus 1, 3 plus 0, 0 plus 1, 4, 3, 1. This is my new current availability, and P0 is no longer in the system. Now check for P1. With this new availability, can we fulfill 4, 3, 1? P1 need is 1, 1, 2. So E needs 1, we have 4. F needs 1, we have 3. But G needs 2, and but we have only 1. So I cannot fulfill the requirement of P1 at this time. So the system will check for another process. Let's check for P2. P2 needs 0, 3 and 0, and I have 4, 3 and 1. E needs 0, I have 4. F needs 3, I have 3, and G needs 0, I have 1. So yes, I can fulfill the need of P2. So P2 will get executed and terminated. When it gets terminated, whatever resources it was already having will be returned. P2 was allocated 103, so the new current availability will become 4 plus 1, 3 plus 0, 1 plus 3, 5, 3, 4. Now check for P1 again with availability 5, 3, 4. P1 needs 1, 1, 2, and E needs 1, we have 5, F needs 1, we have 3, G needs 2, and we have 4. Now I can easily fulfill the need of P1. So P1 comes next in the sequence and gets terminated. P1 release 1, 1, 2, making the new availability 5 plus 1, 3 plus 1, 4 plus 2, it will be 6, 4 and 6. Finally, let's check P3. P3 needs 3, 4 and 1, and we have 6, 4 and 6. So E needs 3, we have 6, F need 4, we have 4, and G need 1, we have 6. So yes, now I can fulfill the need of P3. So P3 will be the last process in the sequence and will get successfully terminated. The safe sequence is what? P0, P2, P1 and P3. Now what is the conclusion? Yes, there is a safe sequence in the system. Safe sequence means if I can get any sequence where I can fulfill the need of processes one by one, if it is possible, then we can call it safe sequence. We call it safe state. The sequence can be multiple also. It's not mandatory that there is only one unique sequence, but our question is not to find the all sequences. Our question is simply whether there is any deadlock or not, any sequence exists or not. This is how you solve such question in GATE exam. This is a GATE exam question. Now moving forward to problem number 2, minimum resource to avoid deadlock. Let's solve one more question on deadlock. The question is, a system has 3 processes, each requires 2 units of resources R. Find the minimum number of units of R such that no deadlock will occur. We have 3 processes, let's say P1, P2, P3. All 3 processes require 2 units of R each. Okay, and here R is a resource like a printer, CPU or memory. Like unit means if R is a printer, then each process needs 2 printer to get execute. If there are 3 processes and each require 2 processes, then total resources needed would be 6. So we could give P1 2 resources, P2 2 resources and P3 2 resources. If I have 6 printer, I will give 2 to each process and the question is solved. But you have to take care of this word minimum. They have asked, like they are asking for minimum number of resources. This number 6, although it works, but this is not the minimum. Let's start with smaller number and check. Testing with 2 units of R. Let's say I have only 2 units of R and 3 processes P1, P2 and P3. I give 1 resource to P1, 1 resource to P2. Now there is a problem. P1 needs 1 more to get executed, P2 needs 1 more to get executed, and P3 needs 2 more to get executed. So all 3 are in the block state. So P1 says I got 1, give me 1 more, but where will that 1 more come from? This is the deadlock situation. Now you might think, what if I give both resources to P1 instead? P1 gets both resources, P1 will get successfully executed. When P1 gets executed, both resources become free, then I can give them to P2. P2 executes, then to P3. But this is not always the case. There might be a situation where P1 gets executed and releases 2 resources, P2 gets 1 and P3 gets 1 still. So still there is a deadlock because P2 needs 1 more and P3 needs 1 more. So with 2 resources, deadlock can occur in some cases. Hence 2 is not the right answer. Testing with 3 units of time, like 3 units of R with 3 resources, our simple case would be give 2 resources to P1 and 1 to P2. P1 execute and release 2 resources. Now P2 has 1 plus 1, 2 resources in total. So P2 execute. When P2 execute, 2 resources are free which can go to P3. This works in this case. But let's check another case like with 3 resources. Give 1 resource to P1, 1 to P2 and 1 to P3. Again we have the same problem. P1 has 1 but needs 1 more. P2 has 1 but needs 1 more. P3 has 1 but needs 1 more. Nobody is going to release their resources because of the condition like mutual exclusion, no preemption, hold and wait and circular wait. So deadlock deadlock can still occur with 3 resources in some cases. Testing with 4 units of R with 4 resources, even if in the worst case where like we give one resource each to P1, P2 and P3 using 3 resources, now we still have one resource remaining. This extra resource can be given to any process, say P1. Now P1 has 2 resources, meets its requirement and executes successfully. When P1 execute, 2 resources become free. P2 and P3 can get their required resources and execute. So with 4 minimum resources, deadlock will never occur in any case. So the answer is 4. Now moving forward to problem number 3. This is also asked in GATE exam. So finding maximum demand. The question is, consider a system with 3 processes that shares 4 instances of the same resource type. Each process can request maximum of k instances. Find the largest value of k that will always avoid deadlock. We have given 3 processes P1, P2, P3. They share 4 instances of the same resource type, meaning there is some resource R and we have 4 units of R. Like these 3 processes can execute request k units each. We need to find the value of k, and the value of k should be maximum. Let's start with k is equal to 1. If each process needs only 1 unit of R to execute, then P1 needs 1, P2 needs 1 and P3 needs 1. Like total demand is 3 and we have 4 resources available. Since 4 is greater than 3, we can easily provide 1 resources to each process and all process will execute successfully. So k is equal to 1 works. Now testing k is equal to 2. Now every process says that demand is 2. We have 4 resources in total. One approach, give 1 resource to each process initially using 3 resources. The 4th resource can be given to any process. So k is equal to 2 also works. Since the question asks for the largest value, we cannot say k is equal to 1 is the answer, because we found k is equal to 2 also works. Now testing for k is equal to 3. Each process demands 3 resources to execute. We have 4 resources total and 3 processes. Whenever the question asks for always avoid deadlock, you have to analyze all possible cases. Give 1 resource to P1, 1 to P2, 1 to P3 and 4th resources to P1. Now the distribution is P1 has 2, P2 has 1, P2 has 1. Now sorry, P3 has 1. P1 needs 1 more resource to execute. Since each process needs 3 total, P2 needs 2 more, P3 needs 2 more. But where will P1 get that 1 more resource? The remaining resource are with the P2 and P3. This creates a deadlock situation. So with k is equal to 3, there exists at least one case where deadlock can occur. Since deadlock is possible in some cases, k is equal to 3, like k is equal to 3 is not our answer. Now testing k is equal to 4 or higher. If each process needs 4 or more resources but we have only 4 total, then clearly it's impossible to satisfy even one process fully in many scenarios. This would lead to more deadlock situation. Therefore the largest value of k that will always avoid deadlock is k is equal to 2. So that's it for this video. We will meet in next video. Until then, bye bye.